In this video, you're going to learn how to write electron configurations and orbital diagrams for neutral atoms, how the electron configurations correspond to quantum numbers, how to write electron configurations for ions, and also how to count the number of valence electrons for main group elements. So the electron configuration for hydrogen is shown here. We can see a few different parts. We can see that the main principal energy level is given here. So that's the quantum number n, the principal energy level. We have the subshell here. So that corresponds to either S, P, D, or F, depending on what subshell we're filling. And then the exponent is the number of electrons. In this case, hydrogen only has one electron, so we're going to put it in the lowest energy orbital possible. When we look at the orbital diagram, we see that it has one electron in it, and by default, we show spin up first. So if I was looking at the quantum numbers for this electron, this would correspond to n equals 1, because we're in energy level 1. It would correspond to an angular momentum quantum number, L, of 0, because this is an s orbital. M sub L, our magnetic quantum number, the only possibility for that is 0, because it can range from negative L to plus L, so in this case, the only option is 0. And then M sub S, our spin magnetic quantum number, is positive 1/2 because we have a spin up electron. So we're going to follow the Pauli exclusion principle, which says that no two electrons in an atom can have the same 4 quantum numbers. So every electron in our diagram has a different set of 4 quantum numbers. So now we're going to look at how I write electron configurations using different elements for examples. Remember that for a neutral atom, the number of electrons is equal to the number of protons. And we're always going to be using for now the ground state configuration, meaning that the electrons are in the lowest energy orbital possible. So for now, we're going to use our orbital energy ordering, 1s, then 2s, then 2p, then 3s, then 3p. And we'll see in a different video how we can actually write electron configurations without memorizing this, but using the periodic table instead. But for now, we'll just follow this energy ordering given here. So we're going to follow the Aufbau principle, which says that we fill the orbitals from lowest energy to highest energy. And also Hund's rule, which says that we fill the orbitals singly first before pairing them. So we don't want to pair electrons unless we have to. Electrons are negatively charged, and so they don't want to be with each other in the same orbital unless they have to. So we'll look at lithium next. Lithium has 3 electrons. So when I fill the orbitals, I have 3 electrons in them. I fill them from lowest to highest. So my 1s gets filled, and then I move on to my 2s, and I have 1 electron in my 2s orbital. So I have 3 electrons in total. So this corresponds to energy level 1. It's an s orbital, and it has 2 electrons in it. And then this corresponds to energy level 2, also an s orbital, and this only has 1 electron in it. So if I were to look at the quantum numbers just for this orbital right here, for that 1 electron in that orbital, this would correspond to n equals 2, because it's principal energy level 2. It corresponds to L equals 0, because this is also an s orbital. It corresponds to magnetic quantum number, M sub L equals 0. And then M sub S, because this is spin up, would be positive 1/2. So remember that the S subshell has 1 orbital. That's why you see 1 box, and that can hold a total of 2 electrons. So each box represents a single orbital that can hold 2 electrons. But the P subshell, which we're going to look at next, there are 3 orbitals that make up that subshell. So that can hold a total of 6 electrons. And then eventually we'll look at D and F, which can hold up to 5, or which has 5 orbitals and can hold up to 10 electrons. And then F has 7 orbitals and can hold up to 14 electrons. All right, so we're going to look at nitrogen next, move a little bit farther in the periodic table. So neutral nitrogen has 7 protons and 7 electrons. So if I fill my orbitals from lowest energy to highest energy, I have 2 electrons in the 1s orbital. I have 2 electrons in the 2s, so that's 4. And then I have 5, 6, 7. So remember, I'm following Hund's rule, and I don't pair those electrons unless I need to. So they do not need to be paired up. They're all in their own individual orbitals at this point. So my electron configuration for nitrogen would be 1s2, 2s2, 2p3. Now P can hold up to a total of 6 electrons. However, I don't have to fill the p orbital. In this case, it only has 3 in it. So now I have a total of 7 electrons. If I were to look again at the quantum numbers, we'll just pick this electron right here and see which quantum numbers correspond to that electron. Here I'm in energy level 2, so that would be n equals 2. I'm in the p subshell, so now my angular momentum quantum number L is equal to 1. Remember, 0 corresponds to S, 1 corresponds to P, 2 corresponds to D, and 3 corresponds to F. So n equals 2, L equals 1, and then m sub L, I can have m sub L equals -1, 0, or +1. So we'll call this the +1 magnetic quantum number. M sub L is +1. And then by default, I always show spin up electrons before I put in a spin down electron. So this is m sub S equals +1/2. All right, let's do one more. Let's look at oxygen. So just like nitrogen had 7 electrons, oxygen has just 1 more, so I have 8. So I have 1, 2, 3, 4, 5, 6, 7, 8. So this corresponds to 1s2, 2s2, 2p4, and that's my electron configuration for oxygen. So now we're going to look at ions and see how ions are different. So we saw that neutral oxygen had 8 electrons. So if I'm going to form the O2 minus ion, I've gained 2 electrons to have a total of 10 electrons. So if I write my electron configuration for this one, I would have 1s2, 2s2, 2p, and I had 2p4 for neutral oxygen. If I gain 2 electrons, then I have 2p6. So I have 6, 7, 8, 9, 10 electrons in total. For sodium, if we look at neutral sodium has 11 electrons. So neutral sodium would look like this. We'd have 1s2, 2s2. So I'm just going up the energy ordering for the orbitals. Then I come to 2p. I can fill that with a total of 6 electrons only. So if I put 6 in there, now I have 10 electrons in total. So now I have to move up to the next orbital, which is the 3s. And since I have 6, 7, 8, 9, 10 electrons, I need to add 1 more. So neutral sodium has 11 electrons. If I lose 1, that means I have a total of 10. So the one that's being lost is the outermost electron. So now when I write my configuration for an ion of sodium, I would have 1s2, 2s2, 2p6, and I've lost that electron in the 3s orbital. And you'll notice that the electron configurations for oxygen 2 minus and sodium +1, they look the same. And this isn't by mistake. So as it turns out, these both have the same electron configuration as neon. So if you look at neon right here, neon is 1s2, 2s2, 2p6. These both ions have 1s2, 2s2, 2p6. So atoms gain or lose electrons to become like noble gases because noble gases are very stable. So noble gases have what we call a full valence shell. So the valence shell, the valence electrons, these are the electrons in the highest energy level. So the highest N, the highest principal quantum number. And these are the electrons that are involved in chemical bonding. So these are very important because when we look at chemical bonding, these are the ones that are going to be reacting with other elements to form chemical bonds. So if I look at helium, helium only has 1 quantum number. It's the n equals 1, so that's the lowest by default. If I go up to neon, neon has n equals 1 and also n equals 2. So all the electrons in the n equals 2 orbitals are the ones that are the valence electrons. So I have a total of 6, 7, 8 valence electrons for neon. Argon has n equals 1, n equals 2, and n equals 3. So n equals 3 is the highest energy level. So the electrons that are in the highest energy level are my valence electrons. So in this case, I also have 8 valence electrons. So we'll see that having a full valence shell typically means having 8 valence electrons. And these are the ones that are involved in chemical bonding. And so they're the configurations of the noble gases are very, very stable. So we can actually predict the number of valence electrons for neutral atoms based on their position in the periodic table, based on the group number that they're in. So if I look at main group elements, and this is for neutral atoms, the number of valence electrons is the same as the group number. So if I were to look at lithium, lithium is in group 1A, so it has 1 valence electron. If I skip over and look at nitrogen, nitrogen is in group 5A, so it has 5 valence electrons, neutral nitrogen. If I look at fluorine, fluorine is in group 7A, so neutral fluorine has 7 valence electrons. And the noble gases in group 8A all have 8 valence electrons. So you'll notice that fluorine tends to gain 1 electron. That would give it 8 valence electrons, going from 7 to 8, so it becomes like a noble gas. We looked previously at sodium, and we said sodium loses 1 electron, and so it becomes like neon, which is the previous noble gas. So atoms are always gaining or losing electrons and turning into ions in order to have an electron configuration that is the same as a noble gas.